A tennis ball is struck. It departs from the racket horizontally with a speed of 28 meters per second. The ball hits the court at a horizontal distance of 19.6 meters from the racket. How far above the court is the tennis ball when it leaves the racket? We'll also later find the velocity of the tennis ball just before it hits the court in unit vector notation, and we'll write the acceleration of the tennis ball in unit vector notation. The first part of these problems is always to sketch a picture of what's going on. So I've got a tennis ball. It's struck with some initial velocity that is horizontal, and then it flies through the air being accelerated by gravity in the downward direction. So it's going to gain some velocity. At all points along this trajectory, the x component of the velocity is the same. However, the y component of the velocity starts at 0 because the ball initially has only horizontal velocity. And then as it's accelerated downward, its vertical velocity grows larger and larger. The total velocity is the sum of these two components, the x and the y velocity. That total velocity becomes larger and larger, and it also changes directions too and starts to angle downward. Okay, so I'm going to put the origin right here underneath the ball, and we need to find the distance to x final, and we also need to find this total velocity. Okay, so now let's go through and fill in this chart of all of our initial values. So since we're starting right above the origin, I'll say x initial is 0. X final, we don't know, but, oh, actually, I'm sorry, I take that back. We do know the final position. It's 19.6 meters. The initial velocity, I should probably put that in here first, is 28.0 meters per second, and the launch angle is 0 degrees. 0 degrees above the horizontal. So the initial velocity in the x direction is v initial cosine of theta initial. Well, cosine of theta initial is just 0 degrees. Cosine of 0 is 1. So this just equals v initial, which should make sense to you because the initial velocity is completely horizontal. There is no vertical component. The final velocity is equal to v initial, and you can put the numbers there too if you want, because the acceleration is 0. We don't know what the time is, but we know the time is the same in the x and the y dimension. On the y side, do we know how high above the court it is? No, we don't know this. We are looking for this in part A. Okay. The final position we do know because the ball is struck and it comes down here and hits the court at 0. The initial velocity in the y direction is also 0 because it's given a horizontal velocity. Or if you want to think about it this way, Vyi is equal to Vi sine theta I, where sine of theta I is sine of 0 degrees. Sine of 0 degrees is 0. The final velocity, we don't know because it's going to be growing. Now, we need to know this for part B. Part B isn't asking us just what the final velocity is in the vertical dimension, in the y dimension, but we're going to need both of these components in order to find the final velocity. And the acceleration, well, that is negative 9.8 meters per second squared. The acceleration of gravity, or negative g. We don't know what the time is, but we know the time in the y dimension is the same as the time in the x dimension. All right. So how are we going to find this thing? We don't have this, we don't have this, we don't have time either. So we've got 3 unknowns here. We're going to have some trouble here. But what if we could find time in the x dimension? How can we do that? Well, we know what the velocity is. We know that the velocity stays the same throughout the trip, and we know what the distance traveled is. So we can find the time over here. Usually, you're going to be looking to the y dimension to find time first, and then going back to the x dimension. This is a counter example of that, in which you're finding time in the x dimension. So find time in x dimension. So x final minus x initial equals v I x t plus 1/2 ax t squared. Well, thankfully for us, the acceleration is 0, so this term goes away. We start at the origin, so this goes away. So v final equals v I x t. We also know that the initial velocity in the x direction is just the initial velocity. So time then is equal to x final over v initial. X final is 19.6, v initial is 28. You can throw the numbers in. I don't want to deal with the calculator, so I'm just going to leave it there. And now come over here and find yf. Okay? So y final, we're finding y initial, not y final. We know what y final is, it's 0. So y final minus y initial equals v I y t plus 1/2 ay t squared. We know the initial velocity in the y dimension is 0. We know the final position is 0. So now I have negative y initial equals 1/2 ay t squared. Well, I'm going to take this time and plug it in for t. I'm also going to multiply by each side by -1 to get this negative over to the right. So y initial equals negative 1/2 times x, oops, forgot something. Negative 1/2 times negative 9.8 meters per second squared, that's the acceleration, times time, which is x final over v initial, quantity squared. I should have left this in symbolic terms, because everything else is, so I'm going to do that, just to be consistent. So now I can plug everything in, negative 9.8 meters per second squared times x final, which is 19.6 meters, over v initial, which is 28.0 meters per second, quantity squared. The negatives cancel out, so that's good. So 0.5 times 9.8 times 19.6 over 28 gives me 2.40 meters. That's my answer. Okay, so the next part wants us to find the final velocity right before it strikes the court. Well, in order to do that, so we want to find v, but first we have to find vy. Well, that turns out pretty easy. Vy final equals, I should say vy final. Vy final equals vy initial plus ayt. We know the initial velocity is 0. We also know what time is. We found it over here. So vy final equals ay times xf over v initial. Vy final equals negative 9.8 meters per second squared times x final 19.6 meters over v initial 28.0 meters per second. Over 28, so it's negative 6.86 meters per second. It's negative though. Does that make sense? Well, yes, because it's downward. It's not upward, right? So the question then asks us, find the velocity in unit vector notation. Well, we've got this. We know what the final velocity in the x direction is because it's the same as the initial velocity. So the final velocity, the vector final velocity, is 28.0 meters per second I hat, minus this 6.86 meters per second j hat. Now, if we wanted, we could go on further and say, all right, so I've got Vy final downward, Vx final positive. So Vy is V final is in that direction. I could find what the magnitude is and the direction, but all of that information is buried within this unit vector notation. So we have that. The last part of the problem says write the acceleration of the tennis ball in unit vector notation. Well, this is kind of an easy write down because the acceleration is constant. So the acceleration here is 0 I hat minus 9.8 meters per second squared j hat. That's all it is.